section 5.3 should look pretty familiar to you since we actually went over inverse functions in pre-calculus. If not, that's fine. We'll ring a few bells here. First of all, what we're going to give you is a definition of an inverse function. A definition of an inverse function is if a function g is the inverse of the function f, if f of g of x equals x for each x in the domain of g, and if g of f of x equals x for each x in the domain of f. So what we're saying is if we do our fog and we do our goff is what we called it, that means f of g of x. All right. If we plug them all in, they both equal x. All right. And just a helpful reminder, the inverse of the function flips the x and the y of the function, so it flips the domain and the range. All right. Real quick here, I want to show you that that these functions are inverses of each other. Well, from our definition that we said that f of g of x had to equal x. All right, well, you guys know what you're doing. If I want to know what f of 2 is, what do? You plug in 2 for every x you see in that function of f, right? Well, now I'm saying f of g of x. So that what I'm saying is I want to plug g of x in anywhere I see an x and f of x. All right, so I'm saying I start with f of x, so 2. Now I see an x. So I'm going to plug in the cube root of x plus 1 all over 2 cubed minus 1. Well, the cube root of something cubed is just going to be that thing itself. So I have 2 times x plus 1 all over 2 minus 1. All right, well, if I distribute it through, or actually I could just look diagonal and cancel out, right? So now I have x plus 1 minus 1. X plus 1 minus 1 is just x, so that's good. Hey, that fulfilled 1/2 of our definition in order to be an inverse. Now all we have to check is if g of f of x equals x. All right, so anywhere I see an x in g of x, I got to plug in f of x. So we started out all right. Okay, so we got the cube root of, let's see now, we'll have 2x cubed minus 1 plus 1 all over 2. All right, and then we got to see what we can do. We'll simplify here. I didn't really need those parentheses, but anytime I substitute in, I always like parentheses. These parentheses really don't do anything. Like we can combine these like terms here. So a -1 plus a 1 is just 0. So now I have the cube root of 2x cubed all over 2. We can cancel our 2's out, right? So now I have the cube root of x cubed. Well, we know the cube root of x cubed is just going to equal x. So they both equal, both f of g of x and g of f of x both equal x. So therefore, they are inverses of each other. All right, not every function has an inverse. Remember the horizontal line test. If a function did not pass the horizontal line test, it does not have an inverse. All right, so we said, look, just think about this. The y equal to x squared graph is a parabola, correct? And you'd agree that it does not pass the horizontal line test, which that means it's not 1-to-1. All right, it means that if it's 1-to-1, every x value has a different y value. All right, so we have 2 x values that have the same y value here. And if you think about it, my inverse, all right, my inverse of an x squared is a square root of x function, but if you graph both sides of the square root of x function right here, this does not pass the vertical line test. That's not a function. All right, so if it does not pass the horizontal line test, it does not have an inverse. And that's what this theorem 5.7 says down here. Function has an inverse if and only if it's 1-to-1, and that's what the horizontal line test shows. All right. Now also, if f is strictly monotonic, which means that it either increases or it decreases on its entire domain. So if you think of monotone, somebody talks in the same voice the entire time. All right, well, that would be kind of like a boring function. It doesn't have any curves or anything like that. It doesn't go like this, not wavy or anything. It's just either always increasing or it's always decreasing. All right, it's not doing anything fancy. All right, then we know it will have an inverse because it's going to pass the horizontal line test. So pretty easy here. Does the function have an inverse? So what I want to do is I'm going to graph these for you, and we're going to figure out if they have an inverse. So let's go ahead and let's graph. Let's see. X cubed plus x minus 1. Let's go ahead and graph that and see what we come up with. All right, well, that doesn't give us a very good picture. All right, we'll see what that x cubed plus x and see what we come up with. All right, our graph shows that is going to pass the horizontal line test. I don't think I can draw a horizontal line anywhere here and pass the graph twice. I think we're okay. It's always increasing, so we're going to have an inverse of that function. All right, so let's graph another one. All right, let's see here. Let's graph x cubed minus x plus 1. Let's graph this function and see what happens. All right, when we graph this function, now look, I can actually draw a horizontal line right through here, and I'm going to pass through that function twice. All right, well, that doesn't pass the horizontal line test. Therefore, that is not going to have an inverse. All right, so the first one's going to have an inverse, the second one doesn't have an inverse. When in doubt, just graph it. All right, check to see if it passes the horizontal line test. Easy enough. All right, and you should remember that from last year when we decided whether a function was decided whether a graph was a function by doing the vertical line test, and then we went farther and said, okay, well, we know if that this function is not going to have an inverse that is a function if it does not pass the horizontal line test, and that's what we're reviewing here today. And the last review here, and you'll think this is pretty silly. You should know how to do this. Find the inverse of the function. Well, you should be able to find the inverse of the function. You just switch the x's and the y's, right? So x equals the square root of 2x, or 2y, sorry, I'm switching the x and y's, minus 3. Square both sides, so I get x squared equal to 2y minus 3. All right, add my 3 over. So I have 2y equals x squared plus 3. Divide by 2, so I have y equals x squared plus 3 all over 2. Now keep in mind then that this inverse is going to have the domain and the range of the original function as well. All right, so that was part of the definition up top here for each x in the domain of G. So if everything that was in the domain of here has got to be in the range here. Okay, so hope this helps, and we'll see you in class.